3 minutes.
Are we televising this or some recorded
Webcast. It's like, okay. 15 people are there, yeah. So.
I've never heard that term. That's interesting.
Because you don't want to give it out publicly, because then we get all the crazy questions. We used to do that. We have a chat room. Oh no, we had to filter through to ask all the stuff. We couldn't keep up. It's like,
Or so the person who told the story.
She doesn't know much about cell phone calls, obviously. How often is it something important?
Leslie, you're a deputy project scientist.
I am.
Okay.
I'm proud of it.
So you're a senior research scientist.
Yes.
You're NASA postdoctoral fellow at Ames.
Yes, yeah.
And you're a postdoctoral story, research scientist at story. Thanks for joining us.
Too late, I was going to let him know that we can write.
Check 1 2 1 2 1 2. Check 1 2 test 1 2 1 2 3 4. Check 1 2.
Is this what's going out now?
Yeah.
I'm not getting it good on wireless.
Check 1 2. Hello, test 1 2.
We're ready to go whenever you guys are ready. Take your time.
I'm just not able to get the broadcast from the wireless. You don't happen to have a spare? Oh, maybe I'll try it that way.
Okay.
Check test. Hello. 1 2 test 1 2.
Okay, can we start? Okay. That's good. Okay. Good afternoon. Welcome to the 47th DPS meeting here in National Harbor. My name is Dr. Vishnu Reddy. I am the press officer for the DPS. I, along with Dr. Rick Feinberg, who is the AAS press officer, welcome you all for a very exciting week of science presentations and also press briefings. So today we have the New Horizons team here going to talk to the media about their results. First, we have Dr. Curt Niebur, who is the program scientist at NASA headquarters. Then we have Dr. Alan Stern, who is going to be who is the PI of the New Horizons mission. Then we have Dr. Mark Showalter at SETI Institute. He's a senior research scientist there. Then we have Dr. Leslie Young. She's the deputy project scientist at SORI, and she's on the New Horizons team. Then we have Oliver White, who's a NASA postdoctoral fellow at NASA Ames and a member of the New Horizons team. And we have Dr. Kelsi Singer. She is a postdoc at SORI in Boulder. And finally, we have Dr. Alex Parker, who is a research scientist at SORI. So I'm going to ask Curt to come and make a few brief comments, and Alan will take over from there. Thank you.
Thanks, Vishnu. Oh, sure. So New Horizons has put on quite the show for us, starting with the encounter back in July. And at that time, this was incredibly exciting, not just for the science team, but for the entire world. But today marks another exciting milestone for this mission. This is the day that the science team gets to sit down and start discussing the science results, and not just the results, but some of their initial conclusions, not just within the New Horizons team, but with the broader scientific community. And that is the milestone that really marks the beginning of the scientific process for figuring out what all this wonderful data that the New Horizons mission is still returning means in the grand scheme of things. This is when the debates begin. This is when the heated discussions begin. This is when the entire science community starts staying up throughout the night, batting ideas back and forth. So now we're no longer only going to exhaust the New Horizons science team, we're going to exhaust the entire outer planet science community. So I really appreciate everybody joining us today. I think you've already seen this morning that there are a lot of fantastic discoveries that have been discussed. That pace will continue throughout this week. And then in the coming months and years, we will be joined by people not on the New Horizons team, by the broad scientific community, as they begin their own research and begin stepping forward, publishing papers, coming to conferences, and presenting their ideas to build on what this magnificent team has done. So having said that, I'll turn it over to Alan Stern to kick us off.
Okay, well, thank you, Curt. Let's see if we can go to the first slide. Just Curt. Okay, there. Now, for my presentation, let me start off by saying I want to try to just frame this by talking about grades, because we're all very familiar with grades from going to school. And, you know, we're 4 months past the flyby. I think it's fair to say we can tell that New Horizons gets an A for exploration. All of our flyby plans seem to have succeeded. All the data sets that are coming down are spectacular. When we see images, we see the target right in the middle of the field. When we see other observations, they just look beautiful. But I also think we get a couple of Fs. One F, if you were paying attention this morning, is we get an F for predictive ability. The Pluto system is baffling us. I said for 15 years to this team that we had the benefit of being the 9th, you know, after the first flybys to the first 8, that we should be able to take all that perspective of not expecting river valleys on Mars and not expecting oceans and the satellites of the giant planets and so forth and so on, and maybe get the last one right. Turns out we get an F. Pluto and its system of satellites has really outsmarted us. It's the best bad grade I've ever taken responsibility for in my life. I think we also got an F for planning on this press conference, because it just dawned on me walking over here from the sessions that I'm pretty hungry. And some of you are even eating, and we're going to sit here for another hour and a half before this group gets to go to lunch. So hopefully nobody has a blood sugar problem. We don't get into snarling. But I do have a couple of things I want to say. For those who are new to New Horizons, just a quick, brief overview. New Horizons is the result of many years of the planetary science community pushing to see the Pluto system and the Kuiper Belt explored. In the end, after a fierce competition, New Horizons won in late 2001. We spent 4 years and 2 months designing, building, testing, and ultimately launching the spacecraft in January of 2006. We got a flawless launch on our Atlas V, flew direct descent to Jupiter 13 months later. At Jupiter, we did a science flyby, but our primary objective was a gravity assist to take us to Pluto. That shaved almost 4 years off the flight time. Then we traveled 2+ billion miles from Jupiter, 2.5 billion actually, out across the middle of the solar system into the Kuiper Belt, and intercepted Pluto this summer on July the 14th. And after a 26-year effort, we canceled this old stamp that says Pluto not yet explored. And now we're in the downlink phase. We've only got about 20% of the data on the ground, in part because of the way we designed our telecommunication system, and in part because of the fact that we share the DSN with very many other important missions. It'll take us about another year. And throughout that entire period, you can be frustrated that all the data is not on the ground, or you can just look at it as new presence land every week. That's the way I look at it. In fact, sometimes I think we feel on the New Horizons team like doctors in an emergency room, running to triage from patient to patient to stop the bleeding, and then another patient comes in, another data set. So we're working very hard. We have already had our first publication, as you may have heard earlier, in essentially record time, and a whole suite of new publications by our science theme team leads are going to be submitted next week. Pluto turns out to be hard itself. It's sort of a graduate course in planetary science. I think that what makes it hard is the combination of the vast variety of landforms that we see on its surface, combined with the fact that it's clear that the time domain really matters at Pluto. That volatile evolution, Pluto's elliptical orbit, Pluto's precessing pole, and other factors move snows and other volatiles around on the surface. We also know that the interior has evolved over time. Bill McKinnon can tell you more about that. You heard some things about that in the last presentation. And this is just going to be very tough. I think it's going to take the larger planetary science community some years to digest all of this, even after all the data comes to the ground. We're also perplexed by the satellite system. The dichotomy between Pluto and Charon is stark. They are nothing like one another. You can see that by looking at a simple image of the pair. And yet they have lived in the same environment, and they were probably made from the same materials 4 billion years ago. And I think this speaks to the diversity of what we will find when we explore other planets in the Kuiper Belt as well. Comparing Pluto, Charon, and Triton, 3 completely different objects. If we went to 3 more, who knows what we would learn, but I'll bet it'd be fantastic. So today and tomorrow, the New Horizons team will be presenting over 50 research reports. The first about dozen happened this morning, and that will continue throughout the afternoon, throughout tomorrow, and there's a poster session as well. We've extracted a few highlights, and we're going to be going through each of those on sort of 5-minute cadences over the next half hour, and then we'll take your questions. So first, Mark Showalter is going to say something about I'm not quite yet. I'm going to go down the list. He's raring to go. Mark's going to say some things that are really astounding that we found about the properties of Pluto's small satellites. They are really unlike anything in any system that we have seen before in terms of their rotational properties and some of the other aspects of the system. I won't steal his thunder, but it's a really fascinating story. Then Leslie Young is going to tell you about her area of expertise about Pluto's atmosphere and volatile transport. Particularly, she's going to tell you how, from an Earth-based perspective, we got it all wrong. Our understanding of the vertical structure of the atmosphere of Pluto, its thermal structure in particular, was wrong. Because of that, our decades-long understanding that the escape rate was high and that this was a hydrodynamic escape regime like a comet was wrong, and she'll tell you about the implications of that as well. Then Oliver White is going to tell you about some just spectacular kinds of landforms on the surface of Pluto, including these putative volcanoes that Jeff Moore spoke about earlier. And I think you're going to find that a real highlight. Following that, Kelsi Singer is going to talk about age dating the surface units on Pluto and the discovery that there are many different ages across the surface of Pluto, not just young and old, but also middle-aged. And then finally, Alex Parker is going to tell you about the implications of exactly that and the size-frequency distribution of craters on Pluto and what it has to tell us about the size-frequency distribution of small bodies in the Kuiper Belt that we cannot hope to see from Earth, that we can only probe by counting the size-frequency distribution on Pluto's surface, and how that has big implications for the origin of planets like Pluto and other objects in the Kuiper Belt. So with that, I will turn it over to Mark Showalter.
Thanks, Alan. It's a real pleasure to be here today. I think we can all agree. Let's see, where's the events? I think we can all agree that Pluto and Charon are really the stars of the show, but I'm here to talk about the supporting cast, a bunch of oddballs in their own right, the small four small moons of Pluto: Styx, Nix, Kerberos, and Hydra. You can see them here resolved for the first time. Now, as someone who was involved in some of the discoveries, I got to say it's very gratifying that it's been only 10 years since the discovery of Nix and Kerberos, and the discovery of Styx was only 3 years ago. So to go from little dots in the sky that are lost in the glare of Pluto and Charon to these actual resolved objects is quite gratifying. You can see they're rather smooth. They have a few craters. You can definitely see a few craters. Oops, whoa. Let's go back. Sorry about that. Wrong button. I'm going to stay away from that. Okay. You can see that they are, we've got a few craters on them, but not very many. Mostly they're very smooth. This kind of makes sense when you think about the fact that a single impact is going to raise a cloud of dust. That dust spreads around, but mostly lands back on the object that it came from, so that at any given time, one crater is basically arising and covering up some of its neighbors, so that we only see maybe a dozen or so large craters at any given time. Come back in 100,000 years, you'll see a different set of craters, but it'll look pretty much the same. They're very bright objects, probably water ice. They're a little bit brighter than we expected because Charon is a bit darker as an object. But you can also see they're very irregular in shape. Now, this is not that unusual for small bodies in the solar system, but let me show you a highlight, which is that at least Kerberos and Hydra are actually multilobes, sort of like two objects that collided at very low speed and just kind of stuck together. Now, we have seen this elsewhere in the solar system, but this seems to be saying to us that at some point in the past, there were more than just the 4 moons of Pluto. There were at least 6. And in fact, when you consider that Styx and Nix are extremely elongated objects, roughly 2 to 1 in their ratios, they could easily as well be merged objects that may be merged at slightly faster speed, so you don't quite see the space between them anymore. So we had at least 2 merged objects, possibly all 4. So we had 8 moons in the past, and probably the truth is that we had a whole lot of moons of Pluto in the distant past. You can imagine that when an impact came along and created Charon, that those 2 formed out of all the material in the middle, and the stuff left over was perhaps hundreds of moons. Some of those got tossed out of the system, the rest of them got merged into the 4 we see today. So there's an insight as to how that system came about. So as we were approaching Pluto, we had about 100 days to look at these little moons as they were emerging from Pluto's glare. And that gave us a chance to study the variations, subtle variations in brightness of all 4 moons, and that gives us our rotation rates. Now, what I've shown here, very clearly not to scale, but Pluto and Charon are in the middle in orange, and the 4 small moons, and I painted a little white dot facing into the center. In a normal planetary system, all these moons would be tidally locked with their one face pointing inward to the system. Now, we had shown, based on Hubble data, that tidal locking is not what's going on, but we didn't anticipate what actually is going on. We expected little wobbles, but in fact, this is a sort of sped up illustration of the rotation of the moons in the Pluto system. Hydra, the blue one outermost, is something that tends to catch everyone's attention first. It's rotating in about 10 hours, yet it takes 38 days to go around the planet. Divide that out, it rotates 89 times during every single rotation around Pluto and Charon. The other moons rotate more slowly, but in each case it's in the range of 6 to 10 days, or 6 to 10 rotations per orbit. So this is unprecedented. We simply have not seen a satellite system that does this. Now, we had predicted that the system is chaotic, but that involves a certain amount of unpredictability and a certain amount of wobbling. This is not what we're anticipating. One of the other things we have found is that the moons are tilted. Nix in particular is tilted by 132 degrees. In fact, if you go back, you can see that it's actually rotating. It's rotating backwards. It's not playing now. Okay, but so we have Nix rotated essentially upside down and backwards. The other 3 moons, as Simon Porter will report today, he's recently determined that they're actually tilted on their sides, spinning almost the way Uranus orbits around around the sun on their sides. As I said, this is a chaotic system, but chaos is a kind of a technical term that means something very specific. The way I would describe this system is not just chaos, but pandemonium, and we honestly have not seen anything like this before, and we still don't know what to make of it. So with that, I will pass on to Leslie Young, who will talk about the atmosphere.
Thank you. The results that I'm going to be presenting today are mostly based on to Occultations. Now, Occultations, it sounds like a cult. It comes from the same word meaning hidden. And fortunately, to illustrate New Horizons flying past Pluto, artists made this lovely artist's conception of New Horizons flying into the shadow of Pluto. And so that helps you picture what's going on. We designed the New Horizons trajectory so that the spacecraft would fly behind Pluto and watch both the sun and the Earth set behind Pluto. And while we were doing, and then rise on the other side. While we're doing that, we were using the large antennas at the Deep Space Network at Canberra and Goldstone to transmit up to the spacecraft. We arranged for the sun to also continue to shine in the ultraviolet. So the first result is from the radio experiment, REX, which detected the slowdown of the radio waves from the antennas at the Deep Space Network. From that, you can get the vertical profile of the line of sight number density, and you can pull out temperatures and pressures from there. We found, again, this was not expected, we found significantly different temperature structures at the base of the atmosphere, down to about 10 or 20 kilometers above the surface. The temperature is very similar at ingress and egress at the entry and exit occultations. And we see that also in the solar occultation. And we were fortunate enough, we as a community were fortunate enough that there was also a ground-based stellar occultation observable just a couple of weeks before the encounter. It's just luck. And you'll be hearing later in this week about the results of that and the symmetry there as well. But back to the New Horizons. We had an example of something similar to Pluto with Triton. Triton is also a nitrogen atmosphere like Pluto, also nitrogen on the surface. Triton has a large troposphere, about 8 kilometers, a handful of miles high. That was an expectation coming in, but of course we set up the experiment to measure whatever we can. What we found instead is that on the exit, there was essentially no troposphere at all, and on the entry, a small troposphere, maybe more of what you would call a boundary layer. You might not be terribly surprised to see different temperatures across Pluto's surface, but the details of the structure here are a little surprising. Nobody predicted that we would have the boundary layer over the cold area and the no boundary layer over the warm area. So this is giving us something new. It's telling us something new about the physics of how atmospheres and surface interact on these nitrogen bodies. The next occultation result I'm going to talk about is from the solar occultation. I should back up, I'm sorry, and say that this was discussed by Ivan Linscott this morning, and more detail on the REX experiment will be talked about by David Hinson's talk later today. So Randy Gladstone in this morning's session talked about how unexpected it was, how little nitrogen there was at any particular altitude. There was a lot less nitrogen than we expected. This means that the atmosphere is much colder and more compact. Before we got to New Horizons, we thought that the exobase, basically one way of defining the top of the atmosphere, was 7 to 8 times larger than Pluto. And now we know that the exobase is only about 2.5 times larger than Pluto. Still significant, still an extended atmosphere, but much more compact. And the models that can explain such a compact atmosphere have escape rates that are thousands of times smaller than what the escape rates we anticipated were coming in. This changes our thinking of the long-term evolution of Pluto and its atmosphere and its ices. This is just a snapshot, and it's always dangerous to go from a snapshot from our 15 minutes of collecting data behind Pluto to the last 4.5 billion years, but we're scientists, so that's what we do. And we say, if the current rate going in, we said we thought that the escape rate was large enough that we would lose about half a mile of ices over the course of the 4.5 billion years. With the new rate, it's closer to something like half a foot. So we still might have ices, probably, almost certainly have ices moving around on the surface, but the atmosphere has huge implications for the history of the geology of Pluto as well. And speaking of the history of Pluto geology, the next talk is Oliver White on Pluto geology.
Thank you, Leslie. So, okay, the big development over the past few months in the geology team is that we've managed to generate high-quality topography maps of much of the encounter hemispheres of Pluto and Charon. And this is a critical step because when you can add the third dimension to your images, you get a much better idea of what processes have formed and modified the various terrains and landforms that we see on the surfaces of Pluto and Charon. So for a number of these slides that I'll show shortly, I'll present topography maps that we've generated. I will also mention at this point that any names of named features that we mention throughout this press conference and throughout the whole conference are all entirely informal at the moment. So first we travel to the west of Sputnik Planum, as shown in this little terrain locator map at the bottom left here. Here we find a region of Pluto that shows several large-scale fractures running across its surface in approximately east-west orientation. The most impressive of these is Virgil Poma fault scarp that's shown in the above image here, which is a straight image from New Horizons. And in the lower part of the slide, we show the same image but with a colorized topography map overlain onto it. And in this image, blues are low elevation and browns are high elevation. Now, Virgil Poma is a pretty major feature. It's around 200 miles long, and at its highest, the fault scarp is 2.5 miles high. That's more than twice as high as the Grand Canyon is deep, so this is a humongous feature. Now, all of the faults that we see in this part of Pluto appear to be troughs and scarps, and we interpret them as being tensional. So the fact that there are so many large faults in this part of Pluto indicates that the crust here has experienced a major extension at some point in its history. Next we move up to the high latitudes to the northeast of Sputnik Planum. And here we see a rather surreal terrain that is characterized by these irregularly shaped flat-floored pits, which can reach several tens of miles across and up to 2.5 miles deep. In the bottom part of the scene, we also see clusters of rather smaller pits. Now, as for the larger pits, they seem to be large-scale enough, certainly deep enough, such that we think that they are probably being formed in part by removal of material from the subsurface. They're deep enough such that sublimation of ice from the surface is probably not sufficient to account for their depth. This terrain also has an interesting characteristic in that it appears quite softened. That we think that there may be a deposit mantling the surface here that is muting and obscuring small-scale topographic relief, particularly when you compare it to the rather more rougher terrain up in the western portion of this image. So we may have a complex location here on Pluto where the landscape is being defined both by large-scale loss of material, perhaps into the subsurface, but also a large-scale deposition of material on top of the surface. Next we move to the southern region of Sputnik Planum, the grand nitrogen ice plains that cover much of the encounter hemisphere on Pluto. This part of Sputnik Planum features a pervasive pitted texture, with individual pits tending to reach a few miles across. I don't show topography for this slide because our topography maps are not high resolution to discern these little pits. But these pits are quite a fascinating breed. They can appear individually, but they also form they can join together to form these long worm-like sort of pit chains. We think they may be forming due to sublimation of ice from the surface of the plains. In some places, we see in the left-hand image, we see sort of clusters of these pits that seem to have dark material on the floors. This dark material might be heating the ice underneath and fostering such sublimation. On the right-hand image, we see an interesting location where these chains of pits form these rather amazing swirl patterns that they form a pattern sort of somewhat akin to a fingerprint. We're thinking that perhaps if the ice here is flowing, then we may be getting fracturing of the nitrogen ice here, and the sublimation may be widening these fractures to form these pits. So the patterns that they form here, these pit chains, may therefore indicate perhaps the stress field across the plains here. Finally, we move to two really extraordinary features to the south of Sputnik Planum. These are broad, tall mountains that show summit depressions. At the top left is Right Mons. At the bottom left is Picard Mons. Picard Mons, I should note, is actually beyond the day-night boundary of Pluto as we flew by. So you're actually looking at this image in twilight due to scattering of light by Pluto's thin atmosphere, and it's been brightened so you can make out features more clearly. But this is a case where our topography is absolutely essential to our interpretation of these features as mountains, which you can see on the right here. So we see that both of these mountains are at least 100 miles across. They reach several miles high, and their summit depressions are really quite apparent. Now, the shapes of these landforms are very similar to volcanic shapes that we see on the inner terrestrial planets, but nothing like this has ever been seen of any kind in the outer solar system. So if these are indeed volcanic edifices, and they would form due to eruption of ice onto the surface of Pluto rather than eruption of rock, then that would be really one of the most phenomenal discoveries of New Horizons, and it would make Pluto an even more fascinating and unique place that it has already proven itself to be, and it could potentially open up a whole new chapter in planetary volcanism research, when we have to consider what happens when you erupt ices onto the surface, forming the grand volcanic edifices such as these. Whatever they are, they're definitely weird, and volcanoes is the probably, in fact, maybe the least weird hypothesis at the moment, but that's what we're thinking at the moment. So now I'll hand over to Dr. Kelsi Singer, who will talk to you about impact cratering on Pluto.
Thank you, Oliver. And Dr. Stern reminded me that I should mention that my talk is right after this event, so if I have to run out at the end, you'll understand why. So I'm going to dive in here talking about the really interesting craters that we see on Pluto's surface. And what's shown here is, I guess this laser's not working. It's okay. The size of the diameter of the craters in miles on the lower left, and the informal names. And so you can see, even with this 11-mile crater in the upper left, we're already starting to see a feature that we call a central peak. And some of these larger craters have central peaks as well. But by the time you get to the size of craters like Burney and Simonelli, about 150 miles or larger across, we're starting to get what we call a basin landform. And some of these may even be multi-ring basins, which we see on other places as well. So we can use craters for all sorts of interesting things, and one of the items I'm going to talk about today is using them to get at the ages of the surfaces that these craters are on. So here's a map showing all of the locations of craters across the encounter hemisphere of Pluto, and there's over 1,000 shown here. I'm going to go ahead and zoom in so you can see one of the main features of this is that there's really variable density of craters across the surface of Pluto. So starting with Sputnik Planum, we have yet to find any craters there, even with the higher resolution data that we've been getting back in the last weeks and months. Then the right side of the heart, or East Tombau Regio, we just see a few craters. And then in the terrains to the west of Sputnik Planum, like Cthulhu and what I'm calling this mid-latitude region, and then the northern latitudes, you can see we see quite a few more craters. So putting this all together, I have a plot here that shows a lot of information, so I'll say what's going on here. This is showing the crater densities per size of crater. So on the x-axis we have the crater size, and on the y we have a relative density number. And the high density terrains are all these ones up towards the top. So you can see Cthulhu in red. The mid-latitudes are in yellow, and the northern latitudes are in blue. And then for contrast, that region I mentioned, that's the right side of the heart, East Tombau Regio, that's shown in the white points. And Sputnik Planum would actually be completely off this plot because as of now, we have 0 craters there. And then overplotted on that are these green curves. And those are the predicted number of craters for a given age surface. So you can see these more highly densely cratered terrains are estimated to be around 4 billion years old, whereas someplace like East Tombau Regio is closer to 1 billion. And for Sputnik Planum, we can put an upper limit on its age of about 10 million years, and it's possibly even younger than that. So the main point of all of these curves is that we see a really wide range of terrain ages. So we see really young terrains and really old terrains, but we also see these intermediate age terrains. So that's telling us that there's been ongoing activity or resurfacing of various kinds throughout Pluto's evolution. So that continues with our theme of unpredicted things, because we really weren't sure what would happen when we got to Pluto, and originally we thought that smaller planets would lose their heat early on. So once again, Pluto is giving us a new view of how small planets operate over their lifetimes. So to get these predicted curves, you actually have to know something about the impactor population that's making these craters, and my colleague Dr. Alex Parker is going to tell you about that.
All right, so in addition to giving us insights into the processes on the surface of Pluto and the ages of the terrains, the craters on Pluto and Charon are telling us a lot about the processes of planet formation, and I'm going to tell you how they're doing that. So most of the craters on Pluto and Charon are created by small Kuiper Belt objects. There may be some craters there that are from interloper populations, but those will be a small fraction compared to the dominant source of cratering, which is the Kuiper Belt. In addition to that, the total number of small Kuiper Belt objects that exist today and have existed throughout the history of the solar system is very sensitive to the actual initial conditions of the solar system and of the processes that drive planet formation. So if we can count up the number of small Kuiper Belt objects that currently exist, we can use that to directly test predictions of theories of planet formation. So we've tried to do this for a long time. Before New Horizons, we could use direct observations from telescopes like the Hubble Space Telescope or from ground-based telescopes to count up directly the number of small Kuiper Belt objects. However, we can't go very far down into small sizes. Direct observations have let us get down to a couple tens of kilometers across. And in the last few decades, we've counted up over 1,000 small Kuiper Belt objects in the surveys that we've done and made estimates about what that means for the total population. However, current facilities can't go any further than that. We can't see things any fainter than an object that's about 10 kilometers across or so. So to go further down, we've tried other things, including some indirect approaches. And so one approach that's been tried for a long time and has recently borne some fruit is the idea of looking at a bunch of background stars and waiting for them to dim, much like searching for an exoplanet, when a Kuiper Belt object passes in front of it. The problem with this is that it occurs very quickly. Kuiper Belt objects are very small, so these events are very short. They last about 0.2 seconds. So you have to use a very fast camera to do this, and it's a very tricky observation. But a group using the Hubble Space Telescope's guidance cameras have claimed 2 events that are consistent with 1 kilometer scale Kuiper Belt objects passing in front of the background stars. If you take those 2 detections in the survey that they did, you infer an enormous population of small Kuiper Belt objects. And that had led to changes in the way we thought about how the Kuiper Belt formed. So this is a figure showing the cumulative number of Kuiper Belt objects from large objects to the right and small objects to the left. The white circles are the observed KBOs that we've seen from direct observations. As you can see, we can only come down to a few tens of kilometers. And in the red point is the inferred population of 1 kilometer objects from the occultation observation from HST. Overlaid on this are two sort of canonical model populations. The yellow line is a model that was invented essentially to explain this observation of an enormous population of small Kuiper Belt objects. In it, Kuiper Belt objects form from small primordial planetesimals. So the fundamental building block of Kuiper Belt objects is a small unit. It's about 1 kilometer across. Other recent theories had invoked large primordial planetesimals of 100 kilometers across or so, which helps explain certain features of the Kuiper Belt, like the frequency of large binary systems. So the yellow line traces the predictions of that small primordial planetesimal model. The blue line is actually the shape of the asteroid belt's size distribution. The asteroid belt is also consistent with forming from large planetesimals. So you can think of these two lines as sort of canonically tracing these two different kinds of models of how planets form very fundamentally. So if you go from that and ask what has New Horizons done, New Horizons has counted up craters on Pluto and Charon. These craters came from very small Kuiper Belt objects. In the days of flyby, even in the data that we have now, New Horizons has already observed more craters than we have detected Kuiper Belt objects. So in one flyby, we've already basically got more statistics on what's going on at the small end of the size distribution than we've managed to do from direct observation for decades. And this is what that looks like. These are the Pluto system impactors. They are incredibly inconsistent with that model of small primordial planetesimals. There are far fewer small craters on Pluto and Charon than would be if that model were true. It's also inconsistent with the observations of occultations of those two objects, of those two 1 kilometer objects from HST. Now that doesn't mean that they were flawed observations. Rare outcomes do occur, and it could be that they are probing a population that is not representative of impactors onto Pluto, or it could simply be a spurious sort of outlier detection. But in any case, they are not representative of the Kuiper Belt as a population. Instead, the Kuiper Belt looks like it has a size distribution much more consistent with something like the asteroid belt, which seems to support the idea that Kuiper Belt objects formed from large primordial planetesimals of tens to hundreds of kilometers across, as opposed to small primordial planetesimals of about 1 kilometer across. And finally, this has some implications for the future of New Horizons. New Horizons last week completed the largest most distant substantial course correction in the history of space exploration. It did that to target a Kuiper Belt object in the cold classical region of the Kuiper Belt, basically where these impactors are coming from. Now, if an extended mission is approved and we can actually fly to this object and explore it, it will be the first of this class of object we've ever seen. And if Kuiper Belt objects formed from large primordial planetesimals, this improves the odds that this object that we're flying by is actually a surviving extant relic, one of these primordial planetesimals itself, not something made up of building blocks, but a fundamental building block of the planets itself. This would be the first time we would have an object like this, something truly pristine and primordial that we could visit with a spacecraft. And that's all I had to say.
Thank you. We'll open up for questions. Raise your hand and there'll be a mic coming around from the back somewhere. Mike is going to get it. And then state your name and organization, and then I'll point to you.
Have you given them the mic?
And if you have any questions for Kelsi, please ask early. Okay, Mike. Eric.
Thanks. Eric Ham with Science. I guess my question's for Leslie. Can you explain, I think Randy hinted at this in his talk, can you explain the reasons why the atmosphere is more cold and compact than you expected? I think it had something to do with the energy instead of going into expanding the atmosphere and making it vulnerable to erosion, instead going into making haze, I think is what he was trying to say. But maybe you can restate that. And then also explain what some of the implications are for the long-term cycling of nitrogen on the planet.
Okay, so why is it so cold and why is it so compact? Before New Horizons flew by Pluto, we thought we understood the mechanism for the escape. That basically the ultraviolet light, which ultraviolet photons are higher energy than other photons. they get absorbed easily by small molecules, and the energy in the ultraviolet light basically went into driving off the atmosphere. So there were lots of different ways to calculate this model. You could do hydrostatic escape in an analytic way, you could do Monte Carlo calculations, but the answers all came out to similar escape rates, about 10 to the 27 molecules per second from the whole planet. Basically similar to if you just take the UV energy and you say, how much energy does it take to launch a molecule? What we found instead is the escape rate is much less, and so that energy has to be going somewhere else. And where we think it's going is that it's getting absorbed by these simple molecules, for example, HCN. These molecules, when they rotate, they can emit energy at very long wavelengths, at radio wavelengths, when they transition between rotating faster or rotating slower. So basically, the ultraviolet photons make these small molecules rotate faster. When they slow down, they emit a photon in the radio, and so it's a way of turning, instead of turning ultraviolet energy into the mechanical energy of escape, it's turning ultraviolet energy into energy at radio wavelengths.
I'd like to add two things to that. I don't think this mic is live, but I'll just speak up. Oh, there we go. First, the HCN molecule, which is this really efficient coolant in the atmosphere, was just detected for the first time by radio astronomers. And there's a report by Emmanuel Lelouch later in this meeting, he's not a member of our team, reporting that detection and the abundance of HCN. So that's a very important tie that bolsters our current understanding of how this all works. And secondly, the reason that the atmosphere is more compact is because the scale height is proportional to the temperature. And so when you make it colder, the scale height shrinks. And that is an exponential effect as you go up. And so a little bit of temperature difference, a couple tens of degrees, makes for a big response in terms of the total extent of the atmosphere.
Okay. Emily, you have a question?
I'm going to continue, Emily Lakdawala with the Planetary Society. I'm going to continue with atmosphere. This small atmosphere seems like a huge surprise, and I'm wondering if you had known that it was smaller, would that have changed your science plans? Because it seems like a lot of your approach science depended on a large escaping atmosphere.
Do you want to speak to that? You want me to?
So we did change our plans in 2012 when one of the models said that it was going to be a very large atmosphere. And so one of my last remaining fears, we were looking at all the data sets coming down and going, oh, good. This mode of observing worked. Oh, good, we flew through the shadow of Charon. And my last niggling worry was that we had an atmospheric model in 2012 that said that the absorption would begin before we started our high cadence observations. And in 2012, we added a just-in-case observation in between the Pluto and Charon occultations, just to catch that case. So I would say we designed the occultation. Basically, it's a straightforward. You don't have many knobs to turn except for where you start and where you end. And do you aim for straight down the middle of Pluto? And the answer is yes, you aim for straight down the middle of Pluto. So I would say we added one in case it was large, and it turned out to be small. I don't think we would have changed our observations if we knew it was small coming in.
I would say that the SWAP and Pepsi teams, if they'd known this, if they'd metaphysically known that the atmosphere was compact, they would have argued for us to go closer. But that would have been a very tough debate because for imaging and imaging spectroscopy, going closer actually hurts your ability to gather the data sets that we did.
Yeah, it was definitely a trade-off. Ironically, you would think that flying closer would get you better images, but flying the distance we did gives us a longer amount of time between getting a wide range of phase angles, looking at Pluto in different directions compared to the sun before the occultation starts. And so things like the image that made the cover of Science was only possible because we threaded this line of plasma, flying close for plasma and flying far for imaging.
Leslie?
Leslie Sage, Nature. So this is for Alan and Leslie. Atmospheric collapse was predicted to occur around now. And with this new view of the atmosphere, what do you expect to happen now with atmospheric collapse?
Well, I'll set the stage, and Leslie's world's expert in this, so she'll bring it home. Atmospheric collapse was predicted to occur in the early 90s, in the mid 90s, in the late 90s, in the early 2000s, and about now, and everything in between. And the reason for that is largely because we didn't have the on-site information that we have today, and there are a lot of knobs you can twist in the computer programs that model this response, and there were just too many free parameters. You could kind of get any answer that you wanted. Leslie, you want to talk about the future?
Well, I think I'll mention that there was a groundbreaking paper by Candy Hansen and David Page that showed the importance of thermal inertia. And so by the mid-90s, we knew that Pluto's season, whether it's equatorial or near solstice, was at least as important as how far Pluto was from the sun. And that changed a big view of what we thought about atmospheric collapse. And I would say what this new result means for similar seasonal models is there's a question: how much do you have to include atmospheric escape as part of your calculations of seasonal models? Larry Trafton wrote a beautiful paper called "The Two-Component Escape of Pluto's Atmosphere," and a lot of his argument was based on how the escape rate affects the seasonal cycling. And this says that it's likely that for large portions of Pluto's lifetime, you can that getting that term exactly right is not going to affect your answers. Oh, I'm sorry. You can catch me after this if you want to. If I answered a different question, then you ask.
I noticed. I think this is either for Oliver or Kelsi. I noticed that a lot of the craters seem to be modified, and I'm wondering if they've been enlarged in that modification. Would that affect the crater ages very much, or not?
Sure, we can both talk about this if you want. I guess we can share this guy. So yeah, we don't see very many fresh craters on Pluto. That's probably saying more about the rate of degradation and the rate of stuff moving around the surface, and even tectonics in some cases have modified craters. But it's a little bit more complicated if you look at what kind of degradation is going on to determine whether that would make something look wider or not, because we also have sublimation and redeposition of material. So from what I've seen, it doesn't look like there's actually been very many craters that would have been widened. There are some that you can barely see because they're infilled. But again, that wouldn't change your determination of the diameter, because you can still see the rim. Usually it's the bowl, of course, of the crater that gets infilled first. So it's a good question, but there's nothing really indicating we've had a lot of expansion of any craters. So that wouldn't change our results on that front.
Yes, I would say that issue is perhaps most pertinent in the terrain I showed in my second slide, which seems to be showing sort of this pitting and this perhaps deposition of a mantling material. It wasn't really in the image in the slide I showed, but there are other parts of that terrain that do show quite circular sort of broad pits, and these may not quite be due to subsurface collapse. They may actually be impact craters that have been heavily modified and covered by this mantling material, and that would probably be the one place on Pluto where this issue is most important.
I'll just add one thing. We are still quite trying to figure out exactly where the equivalent rim would be for Bernie, because for basins and multi-ring basins, there's always a little bit of a question exactly where the rim is.
Second.
Thanks. Did you want to go here first?
Yeah, this is for Dr. Showalter. How does your findings of these, the dance of these moons, can you put that in correlation with your Nature article because it doesn't look as chaotic as I was understanding that from that article?
Well, so yes, you're right about that. The system is in fact chaotic. I think mathematically and in every simulation we do, it shows the mathematical properties of chaos. But by spinning rapidly, you actually stabilize your rotation so that the time scale over which you would see chaotic effects is going to be much longer. So that's why we're not seeing necessarily chaotic effects right now. On the other hand, why they're spinning so fast is completely unexpected. We assume that there are tidal forces. Basically, the tides of Pluto create heat when these things spin, and every place else in the solar system where you have a moon close to a planet, it despins because of that tidal dissipation. The one exception is Hyperion, which is in a special chaotic resonance with Titan at Saturn. But we expect tidal dissipation to be playing a role, and how you can have Hyperion spinning around in 10 hours when we know tidal dissipation ought to be acting on a fairly short time scale is what now is the real puzzle. But that's, we assumed speeds comparable to the orbital speed, and that's when you see this tumbling. What we have now is still chaotic, but it's not, doesn't look like tumbling anymore because of the fast spins.
Thanks. Eric Han with Science again. My question is for Oliver about the cryovolcanoes. So you said that there's nothing like them in the solar system, but there have been lots of claims for cryovolcanoes in other places, Ganymede, Titan, Triton. Can you my first question is, can you explain what makes these new ones potentially a first of a kind? And then my second question is you're kind of being a little bit tentative about this. What else do you need to do, or what else can you do to firm up this discovery? Thanks.
Okay. Yes. So yes. Yes, cryovolcanism the term has been applied to various features that we see on certain icy satellites in the solar system. But the thing is that things it's been applied to has generally been low relief features, or perhaps in the case of Enceladus, where we seem to see active cryovolcanism in the form of plumes coming from the South Pole. There's no real surface expression at all. It's coming out of fissures. This is the first time where we see what appear to be true tall volcanic edifices. On Titan, there have been some studies that have tried to show that there may be cryovolcanic edifices there, but they remain a bit controversial, and we're dealing with radar data, so that adds another sort of murky layer to things. Here we have what is visible evidence for tall, broad mountains with summit depressions, and that is really they look really like classic sort of, you could say perhaps shield volcano morphology compared to what we see on the terrestrial planets. So that's really what I think makes them really special. There's nothing of this scale, positive topographic relief of this scale with a summit depression that we see anywhere else in the outer solar system. And yes, as for whether we think they're truly volcanic or not, perhaps in one respect, it's maybe not so out of the question. I mean, we see in Sputnik Planum the cellular terrain we think might be due to convective motions, which perhaps require a heat source under the ice there. So it's maybe not such a stretch to say that we could also have manifestations of heat loss through volcanic eruptions of ices onto the surface. At the moment, we just have bulk morphology to go on and the images. What would be nice is to see if we can get some compositional data there. If we can constrain the compositions of the these features, then we'd have something to work with respect to modeling how this particular ice would behave if it were to be erupted volcanically, and what sort of relief it might be able to sustain. Hopefully, yes. Do you think we might? I hope so. It's I don't know if the fact that it's right, probably, perhaps not. I'm not so sure for Picard Mons, since it's in twilight. It might be quite dim there, but hopefully for Right Mons. Right Mons is also, it's about 200 miles to the north of Picard Mons, and it's still quite close to the day-night boundary. So, yes, hopefully we will, but I'm not so sure at the moment.
We'll take a few questions online.
I want to just add
one
perspective on the putative shield volcanoes. It's just astounding that in all of the exploration that we have done, that the nearest neighbor analogy to these constructs occurs on Mars. You have to look all the way to the other red planet to find something similar. All the way across all the worlds of the middle solar system, we've seen nothing like this. It's truly amazing. It's like something on a terrestrial planet.
Okay. Online questions. Eric, you have the mic.
Okay, thanks. We have quite a few journalists on the webcast. We'll start with a question from LED Sky and Telescope. Sorry, you got it? He asks, I guess this is for Alan Stern. You guys have been using a lot of names, informal names or otherwise, and the question is, what is the status of actual nomenclature submission to the IAU? Is there a list of names for specific features that have gone to the IAU, and if so, when are you expecting to hear some kind of approval or otherwise?
Well, if you haven't noticed, the New Horizons team has been kind of busy this summer and fall. We have not yet submitted these names, and we haven't made a formal submission, but we have been in communication with the IAU about our intent to make a submission. I expect that it will not be this year. We're changing the features, and things are developing so rapidly that we want to let it settle out a little bit and not do this over and over and over again, and we have to thread the needle. There are a certain number of people and a certain amount of workforce, and we are very busily trying to get results out, plan for an extended mission proposal. All the while, it's very time consuming to plan the downlinks and then triage the data as it comes in every week. So we're kind of up to our eyebrows in that, and this is just a lower priority because it can wait.
Okay, this next question comes from Bill Harwood at CBS News at Cape Canaveral, where he wants to return to the ice volcanoes, the cryovolcanoes, and he's asking about the heat source, the power source. Would radioactive decay be enough, or is there some other source of the heat? And how does a body as small as Pluto stay warm enough for that in any case?
Well, yes, probably internal radiogenic heat source is the at the moment, the only heat source that we can really think of, given that sort of tidal heating has probably not had much effect on Pluto. The heat source is perhaps, yes, Pluto is very small. It will have a silicate core. But yes, well, the heat source may have died off quite a bit over the 4.5 billion years of Pluto's existence. Remember that we are dealing with quite very volatile ices at the surface if these are indeed cryovolcanic features. So they wouldn't require as much heat to be mobilized and to erupt onto the surface as rock would for the inner terrestrial planets. So while there's maybe less heat to go around, it can perhaps you get more bang for your buck, I suppose, with the heat that is available, given the nature of these ices that are on the surface, their volatilities.
Okay, this follow-up question actually from Irene Klotz, also on the ice volcanoes. She's asking if Irene is from Reuters. She's asking if you've considered other possibilities that are potentially even weirder than cryovolcanoes for these mountains.
Well, to tell you the truth, I'm having difficulty unseeing volcanoes with these. As someone who did his PhD on volcanic morphologies, when you see a big mountain with a hole in the top, it generally points to one thing, at least on the satellite. So, yeah, it's basically no for the moment. It's kind of the least. While it's crazy, it's still the least crazy idea that we can think of, and it's certainly not out of the question, given the other possible indications of mobilization of ices and indications of internal heat source we see elsewhere on Pluto.
Okay, Irene also has a question for Mark Showalter on the moons. How might the moons have ended up with these strange rotational properties in their current orbits?
Yeah, it's actually very easy to get the moons into those rotational states because, for example, Hydra, although it's rotating very fast, is rotating at a speed pretty comparable to a typical Kuiper Belt object, something out in isolation in that region. So the processes that spin up a typical KBO are probably impacts from other KBOs, and so we can kind of understand that part. The question then is, why doesn't it slow down? It's not so much why is it so fast, but because it's close to Pluto, there's a tidal force on it, dissipating energy. Rotational motion should dissipate over a pretty short period of time, and yet that's not what we're seeing. So that's really the puzzle.
And I want to ask Mark a question, if you don't mind, because I'm not a dynamicist, but if you found one of these rapidly rotating, you might ascribe it to something like a recent impact event.
Yes.
But to find all four going so fast compared to the orbital periods, that's what's really crazy, right?
That's right. I could also add that Hydra is the fast spinner, and it's the outermost. As you go inward, these moons are generally slower, although still very fast. So we could, in fact, possibly be seeing something where, as you get deeper into Pluto's gravity well, the dissipation is more effective, and so these other moons have been slowed down, and Hydra, by being further out, has not been. But I'm just waving my hands here. I don't have an answer yet.
Can we keep going here?
Take one.
Okay. This question is from Kelly Beatty again at Sky and Telescope for Oliver White. Can you use the rifts that you've observed to estimate how much Pluto's interior has expanded, and from that, can you gauge the thickness of the water ice mantle?
Yes, that will certainly be a result that we'll try and calculate at some point down the line, since these things define themselves pretty well. Let's see. Yes, that will be forthcoming. I mean, we can tell. I think at the moment, just based on what we've seen so far, we reckon that these faults probably cause, since there's no giant sort of planet nearby to perhaps sort of help foster any fracturing of the surface. It's all interior, and it may well be the result of freezing of subsurface melt that would cause this expansion that we see in this part of Pluto. So, but yes, calculations will be forthcoming in that once we've mapped them all and got an idea of how much surface displacement is required at each.
Okay, Emily.
One more question about the small moons. Actually, would these spins and rotation states be more like what you see in the irregular moons of the giant planets? And then one other question relating to Kerberos, which is so much brighter and smaller than was predicted before, and why?
Right. You are making an apt analogy to the outer irregular satellites, because the outer irregular satellites of the giant planets have spins that have no bearing whatsoever on their relationship to the central planet. They just spin because they have a spin state, they're far away. Saturn, Jupiter, Uranus, and Neptune wouldn't have no role. It appears that, to a certain extent, Pluto is playing no role in the rotation of these four moons. The trouble is, these are not irregular satellites. They're in-close, they're circular, they're subject to tidal forces. All of these things mean that they shouldn't be acting like the irregular satellites. They should be paying more attention to their parent than they are, would be one way to think of it. Regarding the darkness of, or the not darkness of Kerberos, I think we were doing the right thing in our paper when simply we were based, we took the information we had, which said this object seems to have a large mass and is very faint. The way to do that is to make it dark. It makes it like another KBO. It doesn't make it outrageously dark. It just makes it different from the other moons. But we were pretty sure all along when we would say that if you take away the mass, if it turns out that that mass number is wrong, then all of our arguments fall apart and it becomes just like the other objects. And so what we're learning is that it's tough to determine the masses of these moons. This is a very complicated dynamical system. The mass comes from just the way each moon has little tugs on the others. So what we're learning, I think we'll learn some of that from Bob Jacobson's talk today. The mass of Kerberos is dropping as we get more information, and I suspect in the end we'll just understand that Kerberos in fact had a small mass all along, and therefore it was always a small object, and we just misinterpreted other information.
Okay, Jay, a question.
Jay Pasikoff, as a textbook author, the journalists have asked excellent scientific questions, so as a scientist, let me ask just the technical questions that will go in the textbooks that you are obviously rewriting. Are Pluto, Haumea, Makemake, and Eris planets? And why are half of you saying Charon and the other half Charon?
And that second question is best addressed at a bar.
So is the first one, by the way.
Well, maybe so. That's right. I think that there's a pretty clear appreciation in the room among planetary scientists that objects like this, that Pluto is much more similar to the planets of our solar system than anything else. And while the astronomers don't seem to understand that attributes matter, I think in planetary science, you heard, how many times did you hear the word planet said in sessions? And just keep listening throughout the next 2 days. It's a great empirical experiment to just listen. If you want to talk about that offline, it's fine, but let me just say that I would say that a better takeaway from this meeting would be not just that Pluto's a planet, but it's probably the star of the solar system.
I would just add that I welcome people debating this, and while they debate it, we're going to keep launching missions to explore the solar system.
Okay, and just want to remind you that we do have a press conference tomorrow titled Quantitative Criterion for Defining Planets. So please do come tomorrow.
Yeah,
Rick,
an astronomer's
yeah.
criteria.
Yes.
So it's based upon one variable, as you will see.
Oh, the question here.
Hi, Carissa Cedar. I'm from the Carnegie Science Center in Pittsburgh. I was wondering, thinking about Charon, or Charon, or however you choose to pronounce, and some of the interesting features, namely the dark features, the dark feature at the pole, and the giant canyon that we found. Do we know kind of any hints behind the causes of those? Are they internal? Are they perhaps external from Pluto? Do we know anything about those?
So I'll say a couple things about it. It sounds like Oliver's raring to go as well. First of all, the large depression near Charon's North Pole is not coincident with the coloration region. They're close and there's some overlap, but it's not one on top of the other. So those appear to be unrelated at this early stage. We had an idea, and some on the team may still favor it, that the red stain at Charon's North Pole was a result of material escaping from Pluto's atmosphere, accreting onto the surface of Charon, which some models had predicted before the flyby, and then being converted to these red tholins that Dale Cruikshank spoke about by radiation processes, just as he described. The flaw in that is that now we don't think that there's a significant escape rate from the current day atmosphere. So either that material and that stain happened at some other epoch long ago, or we just have the wrong idea. So we're scratching our heads over that one, and it's a great puzzle.
Yeah, well, as for the fracture belts, basically they're even larger scale than the ones we see on Pluto. They extend across the whole of the encounter hemisphere, and they seem to be even deeper. So at the moment we're reckoning that it's perhaps, again, maybe due to sort of freezing of perhaps a subsurface melt that is causing sort of near global fracturing here, but yes, on a much bigger scale than what we see at Pluto.
Okay. Rick, you have any?
This question is coming from Daniel Fischer. He's a science writer in Germany. He's asking about what's the current thinking on the time frame in which the Charon or Charon producing collision happened, and has that view changed at all due to the New Horizons data that you have in hand?
Well, so let me say, I can speak to that. So because I've done a little bit of work on that with Bill McKinnon and with others in the past. So as Bill said in his presentation at the very end of the morning sessions, the best work that's been done on this has been done by Robin Knupp. And I think it's widely agreed that we needed something between the size of Charon and Pluto to strike proto-Pluto in order to make this amount of material become deposited in orbit around Pluto from which the satellite system could be formed. The problem with that is there aren't very many other small planets in the Kuiper Belt. And there aren't very many objects. I think Charon is something like in the top 10, maybe in the top 5 largest KBOs. So if you model in a computer how long 10 or 12 or 20 of these bodies have to rattle around in order to collide, you find that it's longer than the age of the universe, which suggests that something was very different in the early days. But it demonstrates, and what that might be, we could talk about some other time, but what it, I think, demonstrates is you really cannot get a recent collision to be a probable event. You can't appeal to a young Pluto-Charon to start explaining things like the energy sources in Pluto or other aspects of the system, because you simply can't make it happen to within orders of magnitude in terms of timescale.
Does that same restriction apply to the origin of the smaller moons? Is the fact, there was a question here, I don't remember who asked it, but is the fact that the moons are spinning so fast potentially evidence that the event that created them, the smaller ones, was more recent? Or is that
perhaps I would argue that that's unlikely because they all share the same orbital plane as Pluto-Charon, which suggests that they were genetically linked to the origin of Pluto-Charon.
Yeah. Okay. If there are no questions.
Well, there are more, but I don't know how much longer you want to go.
We'll take 2 more.
Okay. All right, hold on. Let me see here. I'm having to scroll as well as look at the mics. Here's a good one from Irene Klotz, again from Reuters. She's asking if any of what you've seen so far has given you any reason to think that Pluto, like some of the other outer planet satellites, might have a subsurface liquid ocean.
Yes, well, the evidence for that would really be in the big fracture systems we see to the west of Sputnik Planum that yes may well have. The extension implied by these fracture systems does indicate that we may get freezing of subsurface oceans. So yes, that is really the best evidence we have at the moment.
Okay, one quick question.
Okay, here's one from Leo Enright, who's writing in from Ireland, from Irish TV. He says he's not clear how 2014 MU69 can be pristine if you say that the Kuiper Belt objects were born big. Isn't it very small? And also, how does what you're seeing at Pluto's moons help you plan for the encounter with 2014 MU69?
Alex?
Yeah. 2014 MU69 is several tens of kilometers across. The models that have looked at formation from large primordial planetesimals have done so in relatively sort of discrete experiments where you pick a size as the starting point and go from there. And they've explored starting sizes from tens to hundreds of kilometers across. Now, the statement that is pristine is the argument that it is not a collisional fragment. It is one of these primordial chunks that fell out of the solar nebula at the end of planet formation. If you went from the model of Schlichting et al., which grew things from 1 kilometer primordial bodies, which was motivated and supported by this earlier HST observation of small KBOs, 2014 MU69 would have to be the product of further accretion. It is not itself a primordial body, it is a pile of primordial bodies. But if instead you pick one of the other models that is better supports the binary fraction of the Kuiper Belt and seems to trace the impactor population better, an object the size of 2014 MU69 is a perfectly plausible initial size for one of these primordial planetesimals. It falls within that distribution.
Okay, with that, we'll wrap it up. Just a reminder that it's going to be noon tomorrow and not 12:15 like today for the next press conference. Thank you.
Thank you, Vishnu.